Queen is fair game, right? We're going to review shear capacity of plate girders, and we're going to finish. Well, we probably won't finish it. We'll get close. Plate girders. We'll get further, very close. Last time we talked about situations where we pushed the limits. We were pushing the limits of plate girders, and why would we do that? I mean, where can you typically push the limits in a rolled shape? If I had a rolled shape and I wanted to really slender it up, where is usually the fat at most? Who remembers? In the web. In the web. And why is that? Well, it's to roll a beam. You just have to have some minimum thickness there, right? Just to go through the whole rolling process. So almost always, we would love, if we could, to thin up the thickness of our webs. Okay, and our plate girders give us those abilities. Say, wow, we can actually thin this web up. I think I did a calculation last time where we could thin the web by 80% based off a pure shear calculation. It wasn't right, okay? It's not right. Don't do what I did before. But this theory, in theory, if everything kept going perfectly, we could make it 80% thinner and we would still be okay. It would still be satisfactory. And that's what you try to do with a plate girder. You try to really thin this web up. You actually try to tune the whole member. You really, really, really try to thin the web up. And things start changing. Behavior starts changing when you start to thin the web up. We drew pictures a little bit last time, and we had I had a little prop that I showed you what happens when you have a member that with a very, very thin web, an extremely thin web that was under shear. What happens? This web gets really, really, really thin. What happens? It buckled. It buckled. And the buckled shape or the buckling looks something like that, right? At least that's what the first mode looked like. Okay? It looks something like that. Awesome. Now, to talk about this is important. To talk about this, we said, to kind of idealize this or think about that, we talked about it in two different ways. We talked about it, pardon me. Oh, I forgot mine. Yep, working. That's good. So, I talked about using a equivalent or a discretized shape, discretized piece, right? And we took that out, and we said at the dead center we had shears that looked something like that. And if I rotated this until I get my principal stresses, it would look something like that. Remember that? Okay, you can pretend. Thanks. That was compression and that was tension, right? And they were equal and opposite at the center of the beam. And this compression is what led to this buckling to occur, right? Remember that? And I said, you know what? If you don't want to think about these discretized shapes, what was the other idealized situation that we came up with? Bracing. Well, we imagined as if it's a truss, didn't we? We imagined as if that this is a member, and this is a member, we have those shears, and we have this member's in compression and this member's in tension. You with me? You're with me? This is going to be important to today's lecture. Okay? So keep that in your brain. Okay? Keep that in your brain. So, last time, we started talking, we draw this buckled shape. We started looking at different cross-sections away, and the buckled shape ideally would look like, when I had my sandwich bag, it didn't quite look like this. It looked more like this, like a lot of ripples. Okay? That's because that sandwich bag is really, really, really thin, right? And it's very hard to just move it so you just get the first mode. But if I was perfect, or if we had a little better material, ideally you would get something that looked like this first bulge or first buckle that occurred, and then as you loaded it or racked it further, it would start taking different shapes. Okay, and this would be called different modes of buckling. Okay? Okay. Awesome. So, recall that plate buckling, the plate buckling equation is this, and you might not have ever have seen this equation before in your life. I don't know. Probably not. Okay, maybe if you would have taken advanced strength of materials, hopefully this equation would come up, okay, at some point. But don't worry, don't fret. No? Didn't see it? Okay. We'll just delete that from the tape later, okay? Anyway, so this is the equation. This is, you should see it at some point in your career. If you don't, you have now, right? And really, what this equation is it's very, very similar, extremely similar to this equation. So you see this one before? If you had me, you better be saying yes, or we're going to talk after class, okay? Yeah, you've seen this before. We've done this. This is tattooed on the inside of your brain somewhere. I just have to shake the cobwebs off to see it, okay? So this is the Euler buckling equation that's been transformed and changed, and so it's in terms of stress, okay? And in this equation, we had E, and what was E? You've not had your coffee this morning. What was E? Crying. Young's modulus, right? 29,000 KSI. What was K? I haven't covered columns yet. Can't remember. End restraint factor. L. The length between the braces. R. Radius duration. Thank you, the person that's never had me before. And then, at least for steel. And then pi. 3.14159.807, right? Pi. Right? Great. And we can see we have equivalent things over here in the plate. This is the same equation, but it's for plates. Same equation, but for plates. So if we can imagine a plate that's being loaded, and we have some kind of end restraints on those plates. Those may be rollers, those may be fixed, some sort of end restraint on the plates, and that plate's going to want to buckle in and out of the page. Okay? And this critical buckling stress is a function of pi, E, and then Poisson's ratio. Yeah. Poisson's ratio. That has to do with the stress transformation. Okay. You've seen that before from strength of materials. You just probably chose to forget. Okay. And then we got B over T, which is this aspect ratio. It's similar to this KL over R. Well, similar. It's similar to L over R. It's similar to L over R. Okay? K is equivalent or similar to this K. Okay, so they're like inversions of one another. This K is a version of the end restraint as 1 over the end restraint factor. Okay? Okay? Okay, you don't want to remember it. Well, that's nice because we don't have to keep it in our brains very long. So this is the idealized equation, and we're going to start building from that idealized equation and make it make some assumptions, make it a little easier to deal with. So for our case, the capacity will vary based on the angle and the length of the buckle. And this is derived for an axial load, and we don't have axial load in our structures. We have shear. You with me? We have shear. We're going to be using a lot of the same beasties. Okay? And imagine, in a sense, if this is rotated at, or sorry, rotated. This whole thing was rotated. So if instead we're looking at some kind of plate like this. Okay? With some kind of axial load on it, like that. Okay? Hey, it's like the compression strut in that truss we talked about, right? Okay, cool. So for our case, the capacity will vary based on the angle and the length of the buckle. So this angle is important, is a variable. This length is important. This can get to be a very nasty, and then when I say nasty, it's actually more like nasty, okay? Because that's how bad the problem is, okay? Not only is it differential equations, but it's iterative differential equations. Ugh! Stab! Okay? Nasty problem. But of course, we make simplifications, and the capacity is going to depend on the panel size. Okay? So we're going to start defining variables now. Okay? These variables, one variable is A, and the other variable is H. H is our free height. Okay? A is the length of the buckle. The length of the buckle. The thing is how do we know what the buckle is going to be? We don't really know. We'd have to test that. You're right, we don't. But don't worry, it won't keep you up at night. It's not that big of a deal. If we have stiffeners, then we will assume the length of the buckle is the distance between the stiffeners. And we often use center to center, okay, type distances, even though those aren't exactly right, because the stiffener has some finite thickness, right? We usually ignore that, and we assume that the buckle will be in between the stiffeners. That's a really important assumption. Really important. There's going to be some other things that we have to do that force this to be true. Okay? All right? Because one could imagine these stiffeners spaced very, very, very far apart from one another. You could get multiple buckles in between them. Okay? We're going to not allow that to happen. Okay? We're not going to allow it to happen. We're going to limit our A distance, or A over H distance. So and then if our A, and this is something like if A over H is greater than 1, okay? If our stiffener spacing is greater than our height, which is pretty common, okay? Pretty common. But sometimes we get into these circumstances when A over H is less than 1. What's that going to change? It's going to change our angle, isn't it? These angles will all be less than 45 degrees, okay, if you're measuring that angle right there. And these angles, if we're measuring that angle right there, will all be greater than 45 degrees. Does that make sense? Okay, great. Now we're going to go back to that equation, this same equation. We're going to AISC it, put some more variables in it, and less more variables that we're familiar with. We have this critical stress, okay, and we're going to be using B1 and T. And B1 is really this minimum between A and H, okay, and B2, which is over here, this is what we use to calculate our equivalent K, okay? We're going to have a B1 and a B2, and it's really the minimum between A and H, and the maximum between A and H. Now, I have an asterisk by this, because this is a preliminary equation that we no longer use, okay? But if one ever wanted to, or needed to go back to first principles and work a problem, this would be closer. This would be kind of the broken down assumptions, less complicated version of this. Okay? And thank God we have this assumption. This is kind of like our version of an alignment chart, okay, for plates. Kind of like the version of the alignment chart for plates. Just one equation. And believe it or not, there's an equation for the alignment chart for columns. I just wasn't brave enough to give it to you as undergrads, but you'll be getting it in grad school. Yay. Okay, so this is the case of E. This is how we calculate. This is where we would, kind of what we would say would be the mother of all equations that come after it, but don't worry, more assumptions ahead, more simplifications ahead. So we're going to simplify this. by moving all of the B terms to the K sub V calculation. And then AISC makes a few more simplifications, and we get the following equation. We get this C sub V equation. And this C sub V equation, you might not have ever realized, but you've been dealing with it. You've just been always assuming it's 1. You've always been assuming it's 1 because you've been using rolled shapes. In the world of plate girders, it's no longer 1. Okay? We're going to push the limits. See what we can get. So this C sub V now, we're still going to have our... Okay, so here's our equation. It's basically a ratio of T critical over Ty. I don't get too caught up about that. Where Ty is this 0.6 times Fy of the web. Okay? 0.6 times Fy of the web. Then pi squared E, K sub V, 12, 1 minus mu squared, H over T squared, and then we have this tau Y, right? This yield Y. Don't worry, we're not going to use this equation either. Okay? Well, not too much. Not too much at all, actually. And this K sub V is going to be equal to 5 for unstiffened webs. So what's unstiffened mean? No stiffeners. Okay? There's no stiffeners. K sub V is 5. Okay? Or H over T sub W is less than 260. H, height over thickness of the web, less than 260. You can use a K sub V of 5. If you can't, you have to do, if you don't meet this, you have to do differential equations. And in this class, I highly recommend you not to go an H over T sub W larger than 260. Okay? Okay. Now, so if I have stiffeners, I'm going to have A over H down here. What's A again? Length of your buckle, but we're going to force it to be the length between the stiffeners. You're right. We are forcing it to be the length between your stiffeners. Okay? It's going to be forced to occur. And K sub V is 5 for stiffened webs when A over H is greater than 3, or A over H is greater than 260 divided by H over T sub W squared. What? What is this saying? A over H, that's A is really the length between the stiffeners. We're forcing it to be that. If A over H gets greater than 3, what does that mean? A is greater than 3 times H. That's saying my stiffeners are so far apart that I may get multiple buckles in there. So we fix this. If A over H is greater than 3, then we go back, we kind of fall backwards, and we just assume that as if there's no stiffeners there at all. Does that make sense? That's our infixity. Or if I over H is greater than 260 over, it's the same thing. Same type of thing. Okay, so we've got all these numbers, but truthfully, there's a lot of constants in here. Like pi, and E, and mu, and 12, and 0.6. A lot of constants. You with me? So instead of trying to remember all of these constants, they slam them all together, and we get this. 43,800 K sub V divided by H over T sub W squared Fy. These are the same. They're the same. This just has all the constants slammed together. And this is for elastic buckling. If you go back and you remember what the Euler buckling equation was derived for, that's what it was. It was for elastic buckling. Okay? So when we say, okay, we'll come back what that means in a second. Well, I'll just tell you now. What that means is that for this C sub V is going to correspond to this part. Oh, ladies and gentlemen, is the final Snell chart of apocalypse. There it is. Right there. This is Snell chart number 4. C sub V is up here on the y-axis. H over T sub W is what goes on the x-axis, and we have another gamma P and a gamma R. And it looks something like that. Something like this. We're going to have a linear portion and a nonlinear portion. So this is our nonlinear portion. You with me? Awesome. For inelastic buckling, we'll use the following equation. 187 divided by H over T sub W times the square root of K sub V over Fy. That goes, hey, that's the same equation. That's for the linear part. Everybody with me? Awesome. We got this gamma P. We got this gamma R. Notice, gamma P and gamma R are a function of kV. You're with me? So why this is weird or sad or hard, if you're going to do this by hand, and man, when I was your age, we did have to do it all by hand, okay? It wasn't any design aids. Is because now everything depends on everything. Your Snell chart is a function of K sub V. You with me? Okay? K sub V is a function of A over H. You with me? C sub V is now a function of H over T sub W. So as you changed your H, you changed your Snell chart, and you changed your C sub V, which changed your capacity, which changed the area of web we needed. And oh yeah, C sub V also depends on H over T sub W, which is pretty much the area of the web you're dealing with. You with me? What I'm trying to get at is that we only really have a few variables. A, H, T sub W. Oh, that's not that hard. 3 variables. That's not that hard, right? But every single thing about the Snell chart changes if you change any one of these. So imagine trying to work a beam problem with L sub B down here, where every single time you changed your L sub B, your L sub P changed, your L sub R changed, and everything about your moment diagram changed. Moment capacity changed. Kind of be hard. Kind of be hard. Don't worry though. Steel manual will save the day coming up. Okay? That's why I spent all that money on it. So the previous equations describe the buckling phenomenon. Okay, that's cool. And we'll come back more on how to design with it. And I want to ask, is this structure going to fail once it buckles? Once the web buckles? Okay, you're looking at me like I'm crazy. This structure, if I put the load on it here, if I put shear here, right, if I put the load on it there, and this is my truss, and I increase P, increase until my panel buckles, will it fail? Still have a tension member. What will happen once it buckles? Tension member will take any additional load. And it will be as if this member, for additional loads, let's say that P2 maybe, I guess. For P2, it'd be as if this member didn't exist. You with me? Very, very similar concept to what we talked about with event-to-event analysis, right? Very similar concept. Okay? Very similar concept to structural resiliency. Just because a portion of your structure reaches its limit state does not mean that it fails. It just means there's an event, right? There's a change in stiffness. Great. So what does this mean? This is no! The system will not fail until the web buckles in compression and then yields in tension. And ladies and gentlemen, this is what's called tension field action. And if you go out and this tension field action is this concept, this idea that my system won't fail until my compression member buckles and my tension member reaches yield. That's what tension field action is. And if you go out and talk to practicing engineers, if you ever go work in a steel shop, and you start talking to people about tension field action, you will get hair to stand up on the back of their neck because they usually don't get it. Okay? And if you don't get structural, resiliency, then I could see where this would be very unnerving. Right? We're going to let it buckle. What? No, you're not. No, you're not. Yes, we are. It's going to be okay. Does that make sense? So this concept of allowing the compression member to buckle and then the tension member to yield is called tension field action. Prime example for a future essay question on an exam or a final. Now, we're going to recall, and one thing that I kind of blew over a little quick, but I want to just totally stress right now to make sure we nailed it in your brain. This equation for Vn, there's no phi factor, okay, in there, and there should be. Well, if there was a phi in front, there should be. When you go to apply it, you'll use the phi factor, okay? But this equation for Vn is the same equation we've been talking about ever since. I didn't lie to you about the equation. It's 0.6 times Fy of the web times the area of the web. That's the same classic equation. But we always neglected C sub V. We never mentioned it or talked about it. Because our gamma sub P, our gamma, our H over T sub W, for a rolled section was always less than gamma sub P. It was always 1. Why tell you about the monsters underneath the bed if you don't have to deal with them, right? Until you're ready. Ladies and gentlemen, now you're ready. Dealing with all the monsters now. Most of them. Okay? So, C sub V is going to change. These are the value if it's in the linear part. This is the value it's in the nonlinear part. How do you decide where you're at? Well, you have to know gamma P and gamma R. And this is not hard to do if you're given all these things. But when it comes to design, oh baby, it can get nasty. Sounds like a fun project. Okay. Now, that equation that I just introduced you to, that equation that we just talked about, was only accounts for this V sub C buckle. It does not account for the tension field action portion. So our true capacity is going to be whatever capacity is provided by the buckling plus whatever capacity is provided by the tension field action. And we could add these two together, but if we notice there's a lot of common factors, like all of that, we could pull those out of both, right? If we're adding them together, we could pull them out. So we get, this is going to be the design equation. This is a G3-2 phi times 0.6 Fy A sub W. C sub V, again, this is the contribution. This times this is the buckling capacity. This times this is the yield / tension field action capacity. You with me? Okay. Now, one last thing to throw in here. While the mechanics of the problem, as in this idea, this concept, does not require stiffeners to be there, theoretically, one would not need stiffeners to take this into account, theoretically. All of our assumptions, all of these simplifying assumptions in AISC, all of these assumptions so we don't have to work nasty 5 or 10 page differential equations, requires us to have stiffeners. There's certain things that we're going to have to do to allow tension field action to be taken into account. Now let's all wake up a little bit and think about this. I'm not saying that the physics requires stiffeners to be there for you to be able to account for tension field action. It's not what I'm saying at all. But I'm saying the assumptions that we make in AISC to make it from a very, very complicated problem to something that we can do with one line of calculations and a table out of our AISC manual, we're going to have to make some sacrifices to do that. These are like an engineering solution to the problem. Right? This would make chemists or physicists really antsy, right? Because they want to solve it exactly, right? But hopefully we can handle it, right? Okay. When we combine these two expressions, we get a chart that is really Snell chart-esque, really. So if we think about the original Snell chart, and this is what's contribution from just the buckling strength, just the buckling strength. We're going to get a little bit of extra oomph, a little bit of extra contribution from this tension field action. You'll find out you get way more contribution out here in the nonlinear portion than you do in the linear portion. Okay? And hopefully that makes sense. When things get really, really slender, those stiffeners are going to do a whole lot more good for you. Okay? Than when things aren't so slender, just kind of slender. Okay? So, there's an upper limit. Now we get to the rules. All of these rules that we have to satisfy. There's these. The next couple pages are pretty much rules. Okay? So we're going to trade all these rules instead of doing differential equations every time. But there's an upper limit to the panel ratio. A over H has to be less than or equal to 260 over H over TCW squared, and has to be less than 3. Okay? What's A over H again? What's A? Distance between the stiffeners. What's H? Height of the web. Right? Maybe I jumped in a little bit early with this because there are a bunch more rules that we're going to get to. But design of girders with tension field action can be challenging. And this is what I pointed out before. As the shear strength is a function of H over TCW and A over H. Notice there's an H here and there's an H here. Okay? Those three equations, but everything depends on everything. Nothing is an independent equation. Okay? That's the bad part. Therefore, as you change any one of these, changes everything else. So, this is probably one of the most valuable charts, table 317, in your AISC manual. Okay? The way this chart works, we'll zoom out here. The way this chart works is we have H over T sub W on the y-axis. We have A over H on the x-axis. And then we have BVN over A sub W. Shear divided by the area of the web. The way this works typically is you usually know your load and you have some idea about your area of your web. So you usually come in here with some stress. And that stress means your answer has to be somewhere on this curve. Okay? And then you come over here with H over T sub W. what's that again? Height divided by the thickness of the web. And you come over here and you meet these two up until they meet. And then you come down here, and this gives you an A over H. What's A over H again? What's A? This is between the stiffeners. So if you already know H, because you had to get this, and you already know H down here, this means that it allows you to solve for A. Does that make sense? Okay? And we'll also notice, well, anyway, that's what this table's all about. That's how it works. And it has this lower bottom on it. Okay? Lower bottom. They won't allow you to go below it. Okay? And this is for if tension field action is included. Does that make sense? If you're using tension field action, and if you're using an FY at 50 KSI, this is what you're going to use. Now, this is real important. Notice the word not in huge, bold-faced type. You may even want to box that or underline it or something. Because if you use the wrong chart, you will get the wrong answer. Okay? And this is if tension field action is not included. So you're not using tension field action. You're only using that first term. You're only using V sub C buckle. Okay? And this is if you're using both. And these two charts are for 50 KSI, and these two charts are for 36 KSI. And oftentimes you can interpolate it in between the charts, okay? And you oftentimes have to guesstimate in between the lines where you're at, because it's rare that you come up with 18 KSI on the nose. It's like 19.5, right? Some number like that. Is that making sense? These charts make your life so much easier. Okay? Okay. Now, like I said, now I have to go through all these rules. All these rules that we have to follow. Because we took a really, really crazy, complicated problem and we made it so you can work it with a table. And there's some cost at that. Okay? So, AISC does not allow tension field action in the following circumstances. If I have a member, and I have all these stiffeners in here, the end panel on one of these members, on a beam, tension field action is not allowed. Now, does that mean we can't, there's no capacity there? No. It means tension field action is not allowed. So what do we do? What's that? Use the table doesn't allow tension field action. Another way you can think about it is ignore this term. Ignore that term. Just use the V sub C buckle. Okay? It's not allowed there. And the reason why is little testing's been done on this. So AISC forces you to just use the buckling capacity. Also, there's some assumption about load being transferred or capacity being transferred between adjacent panels. Okay? And so there is no another adjacent panel next to it. So what you do. It's not allowed when A over H is greater than 3. That's when the stiffeners get so far apart they're not really stopping these buckles or limiting these buckles. There'll be lots of buckles in between. Or when A over H is greater than or equal to 260 over H to W squared. It's not allowed when 2 times the area of the web divided by the area of the flange in compression plus the area of flange in tension is greater than 2.5. Not allowed. Why they use this is that they're relying on this is forcing your flanges to, or your web to not be huge compared to your flanges. Okay, that's what this is about. It's forcing a certain ratio. And then your H over B sub B of your flange in compression or tension has to be, if it's greater than 6, then again it's not allowed. That goes into some of the assumptions. If we fail any of these, then we just use the buckling strength of the web, or we just use the table on the left. Yeah? Not the end of the world. It's no big deal. We just cannot count on that extra boost. Also, transverse stiffeners must meet this rule. B over T has to be less than or equal to 0.56 E over Fy of the steel in the stiffener. Okay? Can't be too long and thin. That keeps them from buckling. This last page, see how far we get. We can use the same truss model to actually find out what area of stiffeners we need. Everything you should know, pretty much every single thing in this equation except for maybe this D sub S term. We're going to use 1 when the stiffeners are in pairs on the web. That's when there's a stiffener on, here we have a web and we have a stiffener here and a stiffener here. We're going to use 1.8 when we only have an angle stiffener. We're going to use 2.4 when we only have a single stiffener on one side. Why would you ever want to just put one stiffener on? Aesthetics, minimizing welds. Both are good reasons. Okay. This equation takes care of all the strength requirements, but not stiffness. And there's 2 stiffness equations. One of them is I of the stiffener is going to be greater than or equal to JB T sub W cubed. B is the smaller dimension of A and H. These are all just rules. Rules. And you have to find I of the stiffener. Well, how do you calculate I of the stiffener? Well, I forgot J is this term. This is the J term right here. Again, just a bunch of easy calculations. And I of the stiffener is, you think of the web, think of the something going through the web, and this is your H, this is your B, you take a 1/12 BH cubed of that stiffener. And in this case, if you only have a single-sided stiffener, it's 1/12 BH cubed plus ADY squared, where again you assume your center is at your center of your member, center line of your member. Okay, so for your dy, this is for your dy squared calculation. It's just dy. Okay. Okay. Mark out this last equation because it changed.